In the last part of this chapter, we will try to understand applications of operational amplifier. There are 10 different applications, and all these applications are very important with respect to your board exam. Okay, so in the previous video we tried to understand the concept open loop gain and closed loop gain, and accordingly we have constitute this formula. AOL represents open loop gain, AOL, which is V0 upon V, and V is what is the error voltage, which is the difference between the two input voltage. Okay, and ACL is output voltage upon input voltage. The first application we will try to understand is op amp as inverting amplifier. Okay, op amp as inverting amplifier. See, of course, as I said, there are 10 different applications of op amp, and all these 10 different applications will have 10 different circuits. So you have to understand the logic of designing a circuit from the name itself. Okay, see, what happens is you have to use, there are two terms, inverting and amplifier. In the previous video, what we understood is, in open loop gain, the gain is infinite, and when the gain is infinite, the output will be either plus VCC or minus VCC, plus saturation or minus saturation. So it cannot be used as an amplifier. For op amp to be used as an amplifier, the gain should be finite. And when the gain, how the gain can be finite? By applying closed loop gain. That means there should be a feedback resistance connected from output back to the input. Okay, so what we will do is, let us draw the diagram. Okay, there are two terminals, inverting, non-inverting. There are two power supply, plus VCC, minus VCC, and then this is the output voltage. Two terminals are there. Now out of that two terminals, we have to use it as inverting amplifier. So inverting amplifier, we have to connect the non-inverting terminal to ground, and input should be applied to the inverting terminal. Let that input be VI with respect to ground. Okay, and as we are using it as an amplifier, the gain should be finite, and for gain should be finite, we have to connect some part of the output back to the input through a feedback resistance RF. Okay, and this is RI. Okay, the current here is II, and here the current will be IF. And we know, when op amp is connected in inverting mode, what happens at this point? At this point, these two current will cancel each other. So current and voltage at this point will be zero. Okay, the current and voltage at this point will be zero, which is called as summing point. Okay, which is denoted by summing point S. So this point, summing point, is at virtual ground. That means voltage and current at that point is zero. Okay, so here what we can see is, from the figure we can say, see, what happens is, when Vi is applied, current I1 will flow up to summing point. Now just look at the ideal characteristics. What is the third characteristics? Input impedance is infinite. That means resistance offered by the input side of the operational amplifier will be infinite. So what happens is, no current will flow through the op amp, of course, right? No current will flow through the op amp. All the current will flow through the feedback resistance. Okay, so from the figure we can see that the same I1 is the same current which is flowing through the RF, which is IF. So from the figure we can say II is equal to IF as input impedance of op amp is very high. Okay, input impedance of op amp is very high, therefore we say II is equal to IF. Now what is II? II is the current flowing through input resistance Ri, and this Ri is connected which two points? This point where the input voltage is Vi, and at the summing point, which is at virtual ground. So it will be VI potential difference divided by current, right? Or divided, current will be potential difference divided by resistance. So VI minus the potential at this point is 0, as summing point is at virtual ground. VI minus 0 upon Ri, or I can say it is VI upon Ri. Similarly, what is IF? That is feedback resistance, feedback current. Feedback current is current flowing through RF, and RF is connected between which two points? Summing point and the output voltage. So summing point, that means potential difference divided by resistance. So it will be 0 minus VF upon, 0 minus V0 upon RF, or it can say minus V0 upon RF. Okay, and as we know that II is equal to IF, so we say VI upon Ri equals to V0 minus V0 upon RF, or we say V0 is equal to minus RF upon Ri into VI. So this is the output voltage equation, and closed loop gain ACL is V0 upon VI, so it is minus RF upon Ri. So gain in case of inverting amplifier depends upon the two resistance, the feedback resistance and the input resistance, and this minus sign indicates that there is a phase shift of 180 degree between input and output when op amp is connected in inverting mode. I hope you have understood. Next, we will try to understand numerical based on op amp as inverting amplifier for that particular application. See, the diagram will be mentioned, but you have to understand this thing, that nowhere in the question it will be mentioned as the circuit is of inverting amplifier. You have to see the circuit and you have to identify whether it is an inverting amplifier or non-inverting amplifier or adder or subtractor. So that is why it is very important that you understand the logic behind the circuit. See, when I say op amp as inverting amplifier, that means between input and output, the output should be inverted, that of input, and that will happen only when the input is applied to the inverting terminal, and when the input is applied to the inverting terminal, the non-inverting terminal should be grounded. So that is what we have to see in the circuit diagram. Okay, so in this circuit diagram, the non-inverting terminal is grounded and input voltage VI is applied to the inverting terminal. So from the figure, just looking at the figure, we can understand that the circuit is connected in inverting mode, and moreover the output is connected back to the input through a feedback resistance, right? So that means it is inverting amplifier. Okay, so op amp as inverting amplifier. In the previous video, when we obtain the output voltage equation for the inverting amplifier. Okay, so what is the output voltage equation? V0 is equal to minus RF upon Ri into Vi. So in this circuit diagram, what is RF? RF is 47 kilo ohms, that is 47 into 10 to the power 3 ohms. What is Ri? Ri is 4.7 kilo ohms, that is 4.7 into 10 to the power 3 ohms. And Vi, so we have three different values: 0.39, Vi is equal to 0.75, and Vi is equal to 1.14 volt. So we have to calculate output voltage for these three different values of input voltage. So you just have to substitute the values one by one and you can easily find out. So output voltage is minus RF upon Ri. So what is RF? RF is 47 into 10 to the power 3. And what is Ri? 4.7 into 10 to the power 3 multiplied by what is the first input voltage? 0.39. So this value will be, this is 10 multiplied by 0.39 will be 3.9 volt. Of course the output voltage will be minus, because as the input is positive and you have converted into the inverting terminal of the op amp, the output will be 180 degree phase shift, the output will be negative, so minus 3.9 volt. Similarly, V0 is equal to minus 47 into 10 to the power 3 upon 4.7 into 10 to the power 3 multiplied, what is the second input voltage? 0.75. This cancels, this is 10, so this is minus 7.5 volt. Okay, second. And third is minus 47 into 10 to the power 3, 4.7 into 10 to the power 3 multiplied by 1.14, right? 1.14. So again this value will be 11.4 volts. Of course the first answer is right, the second answer is also correct, but our third answer will be wrong. Of course I have to mention it as minus 11.4. Minus sign will indicate there is a phase shift of 180 degree between input and output. Still my answer minus 11.4 volt will be wrong. Now so the important point to be noted is the supply voltage which is given to the operational amplifier. What is the supply voltage? Plus 10 volt, minus 10 volt. So what is the maximum value of output voltage which it can reach? Either plus 10 volt if it is in the positive direction and minus 10 volt in the negative direction. Output cannot be more than the supply voltage. Okay, output cannot be more than the given supply voltage. So here what we will say is this answer is wrong. The output voltage will, of course it will increase, it will keep on increasing to the maximum saturation. That means the output here will be minus 10 volt. We will write, since the circuit goes into negative saturation. Since the circuit goes into negative saturation, so that is how we have to write the answer. This question, most of the times this question has come for 3 marks. So again it is very important. Okay, formula 1 marks, and then you have to solve or substitute the values and you have to get the answer. So this is the numerical based on op-amp as inverting amplifier. I hope you have understood. Next, the next application is op-amp as non-inverting amplifier. Again you have to design the circuit taking clue from the name, non-inverting amplifier. So when you draw an op-amp circuit, there are 2 terminals, inverting and non-inverting. Okay, inverting and non-inverting. In this case we will apply input to the non-inverting terminal. Okay, and then we have to use it as an amplifier. So whenever the circuit has to be used as an amplifier, the gain should be finite. For the gain to be finite, you have to connect some part of the output back to the input through a feedback resistance RF. There will be 2 power supply, plus VCC, minus VCC, and this will be V0. And one more important thing is, as the input is applied to the non-inverting terminal, the inverting terminal should be grounded. Okay, so this is how we design op-amp as non-inverting amplifier. I am drawing the same circuit but in a different manner, so that the circuit, the output voltage which has to be obtained that becomes much more easier to understand. Okay, so this is the circuit diagram. Both this circuit diagram are same. Okay, just look at this. I've just inverted the position of the terminals, inverting and non-inverting terminal. Now inverting and non-inverting, we have given input with respect to ground. So that is what I've done. I have the potential at this point AB, VB, and there will be some part of the output will be connected back to the input through a feedback resistance. This is the RF and this is the point, and from where Ri is going to ground. Okay, so this is the same circuit. Now it becomes very easy for you to understand the derivation which will be trying to obtain for output voltage. Okay, now this is a op-amp as a non-inverting amplifier, and you know the difference between the two input voltage, the difference, of course, differential gain is infinite. So the difference between the two input voltage is called as error voltage, V error. We sometimes specify as V. And what is V here? V is VB minus VA, and it should be equal to 0 because it will be output, it will be output voltage upon gain, and gain is infinite. Anything divided by infinity will be 0. So VB minus VA will be equal to 0. Now I can say VB is equal to VA. Now what is VB? VB is equal to VI. And what is VA? VA is the potential at this point, and this to obtain the potential at this point, see what happens is here the current will flow like this. At this point there is a bifurcation, so current should flow like this. But as the input impedance of op-amp is very high, as the input ideal characteristics of op-amp, as the input impedance is infinite, no current will flow through the op-amp, all the current will flow through the RI. That means two resistors are connected in series and same current is flowing through the resistance. They form voltage divider arrangement. And what is the formula for total voltage divider arrangement? Total voltage. So if you want to obtain voltage across VA, that means voltage across VA with respect to ground, and between VA and ground there is RI. So you have to obtain the voltage drop across RI. So for the formula for voltage divider arrangement is total voltage, that is V0 divided by total resistance RI plus RF multiplied by the resistance across which the voltage is taken. So for calculating VA with respect to ground, you have to calculate voltage drop across RI. So it will be RI. Okay, let this be equation 1, let this be equation 2. Substituting the value of 2 in 1, what we get is, substituting the value of 2 in 1, VI is equal to V0 upon RI plus RF multiplied by RI, or I can say V0 is equal to RI plus RF upon RI into VI, or I can write the same equation as 1 plus RF upon RI into VI. So this is the output voltage equation for op-amp as non-inverting amplifier. And what is the closed loop gain? ACL. ACL is V0 upon VI. So in this equation, what is V0 upon VI? It is 1 plus RF upon RI. So even in this case, non-inverting amplifier, the gain of the amplifier depends upon the feedback resistance and the input resistance. So this is op-amp as non-inverting amplifier. I hope you have understood. Now numerical based on op-amp as non-inverting amplifier. Of course, the circuit diagram will be given and you will be asked to calculate the output voltage of the given circuit for different values of input voltage. 3 different values of input voltage are given. The input is 2 volt, 3 volt, 4 volt. Input resistance Ri is 2 ohms, feedback resistance is 6 ohms, and very important, the power supply plus 15 and minus 15. The maximum saturation level is plus 15 and minus 15. So you need to calculate the output voltage. So what is the formula? In the previous section we derived output voltage equation for op-amp as non-inverting amplifier, which is 1 plus RF upon RI into VI. What is RF? RF is 6 ohms. What is RI? RI is 2 ohms, and VI is 2 volt. VI is 3 volt, and VI is 4 volt. Okay, 4 volt. So we need to calculate the output voltage. Just substitute the value and get the answer. So V0 is equal to 1 plus 6 upon 2 multiplied by Vi, that is the first value of Vi is 2. So 6 upon 2 is 3. Okay, 3 plus 1 4, so gain will be 4, so 4 multiplied by 2, the value will be 8 volt in the first case. Next is V0 is equal to 1 upon 6 by 2 multiplied by 3, so it will be 4 into 3, that is 12 volt. And the last case, V0 is equal to 1 plus 6 by 2 multiplied by 4, so this will be 4 multiplied by 4, the value will be 16 volt. But what is the maximum saturation level at the positive? It will be plus 15, so answer cannot be more than the input supply voltage, so it cannot be 16 volt, it will be 15 volt. We have to write, since output goes into positive saturation. Okay, so this is how we have to mention it. This question will be asked for 3 marks. I hope you have understood. The next application is op-amp as sign changer. Okay, I will draw the diagram. You have to identify what type of operation will be performed by this circuit. Okay, so this is the circuit diagram, plus VCC minus VCC, this is output voltage, and there will be a feedback resistance which is RF, this is RI, and input voltage connected to ground. So the first look of the circuit tells you what it does, what it tells. Non-inverting terminal is grounded, input terminal is applied to the inverting terminal, and of course there will be a feedback resistance. So when there is a feedback resistance, that means the circuit is going to used as an amplifier, and as the input is applied to the inverting, there will be a phase shift of 180 degree between input and output. That means the op-amp, this circuit is op-amp as inverting amplifier. And in the previous videos we have understood, or we have obtained the output voltage equation for inverting amplifier. So this circuit is nothing but op-amp as inverting amplifier. So formula will be minus RF upon RI equals to, multiplied by VI. Now if in this circuit, if RF is equal to RI, so in this equation, if RF is equal to RI, the value will be 1. So output voltage is minus of VI. What is VI? VI is the input voltage, V0 is the output voltage, and what you can see is, if you are giving input as 5 volt, what you are going to get at the output is minus 5 volt. If you are going to give input as minus 2.4 volt, what is the output? The output will be positive plus 2.4 volt. So what you are giving at the input, same you are getting at the output, that is the voltage level. But what happens to the sign? The sign changes from positive to negative or negative to positive, and that is why we say op-amp as sign changer. If you remember, it's nothing but a NOT gate, right? NOT gate, 0. When you give 0 at the input, you get 1 at the output. When you give 1 at the input, you get the 0. So it complements the value. Here it complements the sign. Okay, if you give positive value, the same amplitude you will get at the output with a negative sign, and if you give negative values, you will get the same amplitude but with the positive sign. So that is what is op-amp as sign changer. The next application is op-amp as buffer. See the diagram here. Now the circuit which I have drawn on the board is, just look it closely. What you can see is input is applied to the plus terminal. Plus terminal is a non-inverting terminal. So input is applied to the non-inverting terminal, and inverting terminal is grounded, and there is a feedback resistance, which is the feedback resistance is provided as a negative feedback. That means gain has to be suppressed. That means the circuit has to be used as an amplifier. So input is applied to the non-inverting terminal, feedback resistance is provided, so it is non-inverting amplifier. And in a non-inverting amplifier, the output voltage is given by 1 plus Rf upon Ri into Vi. Now see the modification which I'm going to do. What I'm going to do is, instead of connecting the output through a feedback resistance, what I will do is I will connect the output directly to the input, and when that happens, the resistance, this input resistance is now insignificant. Okay, so this is the basic circuit diagram of an operational amplifier, which is nothing but op-amp as non-inverting amplifier, where feedback resistance is made zero. Resistance is made zero means the output is directly connected to the inverting terminal. Okay, so now what we have done is we have made Rf is equal to 0. So in this equation, if Rf is equal to 0, V0 is equal to Vi. This value becomes 1 and V0 is equal to Vi. That means whatever be the input voltage we will give, thus we will get the same output with the same sign also. Okay, there will be no change in the sign. The same sign you will get at the output. But if that is the case, what is the importance of this circuit? So we need to understand where this op-amp as buffer will be used. Okay, now suppose there is two circuits, say this is 1 and this is 2. Generally what happens is, for any analog circuit, input impedance should be very high and output impedance should be very low. But some cases, for example in this circuit, say circuit 1, its output impedance is high, and here for second circuit the input impedance is low. Okay, we are talking about the resistance offered by the output side of the first and the input side of the second. So output impedance is high and input impedance is low. Now if these two circuits has to be connected, say 5 volt of this is transferred to the second circuit. But see what happens is, as soon as you connect these two circuits, the output impedance of the first circuit, say I will draw it as a resistance, and input impedance, they come in parallel. Okay, so now as the resistance of this circuit, in output resistance of this circuit is very high, the current which is flowing through this resistance now get a path, parallel path, where there is low resistance. So the current which has to be flowing, which should be flowing through the output of the circuit 1, got a parallel path, and it will flow through the input of circuit 2, which can damage the input circuit also. So for that, these two circuits cannot be connected directly, so they are connected through a circuit called as buffer. Okay, the circuit called as buffer, and buffer is made up of op-amp, and op-amp, the input impedance is high and output impedance is low. That means here at the input side, what it does is the output, the impedance is matched, right? Output impedance of the first circuit and the input impedance of op-amp, both are high, so impedance is matched. Similarly, output impedance is low for a buffer, and input impedance of circuit 2 is low, so here also the impedance match. So basically op-amp as buffer or the buffer circuit is used for impedance matching. This question can be asked as Viva question if that particular experience comes to you. This is a very typical question, that what is the use of buffer if input voltage is equal to output voltage? There is no need to design such a circuit, but when such a situation arrives, the buffer acts as buffer is used for impedance matching. So this is the application of op-amp as buffer. I hope you have understood. Next application of op-amp is op-amp as adder. Okay, see the circuit diagram which I am going to draw for op-amp as adder. This is where we will take the output voltage. Some part of the output is connected back to the input through feedback resistance RF, to power supply plus VCC, minus VCC, non-inverting terminal is grounded, and instead of one input we are providing 3 inputs to the inverting terminal. Let's say the voltage is V1, V2, V3 applied through R1, R2, R3, and when this happens the current will be I1, I2, I3. As the op amp is connected in inverting mode, you can see the circuit diagram, right? Non-inverting terminal is grounded, input is applied to the inverting terminal. So this point is summing point, and summing point is at virtual ground. Okay, so keeping all this thing in mind, we will obtain the output voltage equation for op amp as adder. Okay, now we will write as the input impedance of op amp is very high. What happens is, see this I1, I2, I3 current which is flowing through R1, R2, R3, when V1, V2, V3 is applied, all this current will reach up to summing point S. And as the input impedance of op amp is very high, no current will flow through op amp, all the current will flow through the feedback resistance. Let that current be called as I4. Okay, let that current be called as I4. So as the input impedance of op amp is very high, we can write, what we can write is current is I1 plus I2 plus I3 up to this point. As input impedance is high, no current will flow, the same current will flow through I4, so it will be I4. Okay, so now I1, what is I1 now? I1 is the current flowing through R1, and R1 is connected between which 2 points? Input and summing point S. Summing point is at virtual ground, as this is an inverting mode. So I1 is equal to V1 upon R1. Of course it will be V1 minus 0 upon R1, which will be V1 upon R1. Similarly, I2 is V2 upon R2, I3 is V3 upon R3, and I4 is the current flowing through RF, and RF is connected between which 2 points? These 2 points. Summing point is at virtual ground, so 0 minus V0 upon RF, so it will be minus V0 upon RF. Okay, so what you can see is, let this be equation number 1, let this be equation number 2. Substitute the value of 2 in 1. What you get is V1 upon R1 plus V2 upon R2 plus V3 upon R3 equals to minus V0 upon RF, that is the feedback resistance. Or I can say V0 is equal to minus RF V1 upon R1 plus V2 upon R2 plus V3 upon R3. Okay, so this is the output voltage equation in an op amp as adder when the resistance, all the resistance values are different. If all the resistance value, you have to use this output voltage. If R1 equals to R2 equals to R3, we can write the same equation as minus RF upon R in bracket V1 plus V2 plus V3. One thing I have forgotten, so of course there will be a minus sign which will indicate there is a phase shift of 180 degree between input and output. So if R1 equals to R2 equals to R3 equals to R, we can say the value V0 is equal to minus RF upon R, V1 plus V2 plus V3. And if RF is equal to R, V0 is equal to minus V1 plus V2 plus V3. That means output voltage is addition of the 3 input voltage. That is why it is called as op amp as adder. And this minus sign indicates there is a phase shift of 180 degree between input and output as it is connected in a inverting mode. So this is the output voltage equation, output voltage equations of op amp as adder. If all the resistance are different, you have to use this formula. If R1, R2, R3 are same, then you have to use this formula, and if all the resistance are same, then you will use this formula V0 is equal to minus in bracket V1 plus V2 plus V3. I hope you have understood. Let us understand a numerical based on op-amp as adder. Okay, in this circuit what you can see is, of course, it is connected in a inverting mode. Instead of 1 we have 3 inputs. Now in this circuit the resistance value, that is R1, R2, R3 and RF, all are different. So what is the output voltage equation? V0 is equal to minus RF V1 upon R1 plus V2 upon R2 plus V3 upon R3. RF is this feedback resistance, R1, R2, R3 are these 3 input resistance, and V1, V2, V3 are the 3 input voltage, and this minus sign indicates there is a phase shift of 180 degree between input and output as the input is applied to the inverting terminal. Okay, so now substitute the value. V0 is equal to, what is RF feedback resistance? It is minus 16 into 10 to the power 3. Of course all these are in kilo ohms, we don't have to specify that value, we can say 16. Then V1 upon R1, V1 upon R1, R1 is 2 kilo ohms, so I can say what is the value of V1? V1 is 0.5 divided by 2 plus 1 divided by 4 plus 2.5 divided by 8. Okay, so this value can be written as V0 minus 16 upon 8. Okay, this value can be written as 0.5 multiplied by 4 plus 1 into 2 plus 2.5 into 1 divided by 8, which will be taken out. Okay, so this is the value. So V0 is equal to minus 2, in bracket it will be 2 plus 2.5. so this value will be V0 is equal to minus 2, it will be 6.5. so 2 multiplied by 6.5 will be minus 13 volt. So output will be the addition of all the 3 input voltage with a gain factor. Okay, the gain factor of course here is of 2. The gain factor is of 2. If you keep all the values of resistance same, the output voltage would have 6.5, which is the addition of all the 3 input voltage. So it can be used as an adder or it can be used as an adder amplifier. Okay, so both the operation can be performed. I hope you have understood.